So as we begin our review, we've talked a lot about units over the course of our study, and the fundamental SI units are important to remember, and you need to remember each of these. We know length is the meter, mass is the kilogram, and this is the only one with a prefix, kilo, time in seconds, and then current, remember how it's amperes. It's not coulombs of charge, right? We actually derive coulombs from amperes. And then temperature in Kelvin. And then the mole is the SI unit, and that's this many molecules, 6.02 times 10 to the 23rd molecules. So as we get started, let's review this here. How many millimeters are in 6.2 megameters? On your IB data booklet, you'll have all the prefixes, and so you got to remember how to use them. So go ahead and calculate. Remember, you have to go to the base unit first with no prefix. You go to meters and then go to megameters. So go ahead, pause the clip, and set up your brackets there, and then when you're ready to check, you can hit play to continue. All right, so we should get 6.2 times 10 to the 9th millimeters is the conversion. First, we get into meters, and then we can convert to millimeters. And 1 millimeter is 10 to the negative third. I think I had something that's negative third. So millimeters. Down here, mega is the prefix, mega, right? So the prefixes have to be really on the top and bottom. It's just the numerical value up here, mega down below, and then here milla is the prefix, and then milla down here. And so the top and bottom are equal to each other. Our units, meters, cancel out, and or megameters rather, cancel out, and then we're left with meters. And then here meters, and then we have meters down here, but then millimeters, so our meters cancel out, and we're left with 6.2 times 10 to the 9th millimeters. All right, so orders of magnitude are very, very helpful for us, and we use these way back at the beginning of our study. It's a value rounds to the nearest power of 10, and look at how many zeros. So let's go ahead and do this for the Earth to the Sun, and let's get in orders of magnitude how many meters this is. And so we reviewed in class how we take this value and we take the log of this value. And so the log of this value is 11.17. So therefore, we can get the orders of magnitude. 10 to the 11th meters is the orders of magnitude for this value. And let's compare that then to the altitude of a rocket ship heading into space, 65,202 meters. So if we do the log of that value, we get 4.8, which rounds to 10 to the 5th. And so this is really nice because now we have something to compare this with. We have, the orders of magnitude in meters Earth to the Sun, and we have this value with the rocket ship. And that's really nice because now if we wanted to compare those, we subtract those, and it's 10 or 6 orders of magnitude different. And we can compare this to other things. For instance, the size of a nucleus is 10 to the negative 15th meters. So we can see, the difference in orders of magnitude between all of these. So really helpful way to estimate, a helpful way to, evaluate, what we have. And that's good there. One of the things that will be helpful as well, and I want you guys to memorize at least these, is to have some ideas of some orders of magnitude. I'm going to have you guys memorize the orders of magnitude for the age of the universe, the distance of the observable universe, 10 to 26 meters. The size of a nucleus, someone pointed out in class, is actually on the data booklet, which is nice. And then the mass of the universe. And so just commit those to memory. Most of these you should be able to kind of figure out, well, some of them at least. Here is the period of a heartbeat, which is order of magnitude of 1, which period remembers the cycle, so in seconds. So 1 heartbeat a second, about 60 a minute. Okay. All right, so it's also important to remember how to deal with systematic and random errors. And so remember, random errors if a measurement is repeated many times, it can be expected that the measurement will not be too large, or will be too large as often as it is too small. So if we get an average of these measurements, the error will tend to cancel. And so we get values around a value, and we average those, and we got that. Now, systematic is most common source in incorrectly calibrated instrument. And so it's consistently off by a certain amount. So the whole data set is shifted over. And, we don't have with that shift, we consistently get an answer that is away from the acceptable answer. And so, yeah, we see this, we use the neutrino example where they thought the neutrinos were going faster than the speed of light, but then they figured out that there was a couple issues with the equipment and turned out to be actually slower than the speed of light. And so through their study, they ended up finding that. And so we've got that there. So in that experiment, basically what happened is they were very precise. They had very, close values, but they were off the accepted value because of the systematic error. Once they fixed it, they got something very precise, which was slower than the speed of light. Now, this would be an example of having random error where you're measuring, you're not so precise where you're getting the same values, but if you average them, you get around the accepted value. Here, you're neither precise nor accurate. So we can be very precise in measurements if we use certain instruments. This is a caliper, and this is giving a digital readout of the value of measurement. It's interesting. We, in class, I went ahead and set up or showing a measurement there in class of what was going on, and the precision of measurement is just dependent upon, the kind of instruments you use. And so, we have this one here with the caliper where we can be very precise. And so we've got that there. So what's the uncertainty in the meter stick? Well, what we do is we look at the markings, right? So the most precise marking we have here is a millimeter. And so that's 0.1 centimeters. And so what we do is when we measure, we take half of the tick mark. So the tick mark is 1 or 0.1, so the uncertainty is plus or minus 0.5. So if we measured something like this, where it's, like say 2.2, and then a little bit more, we guess to the next digit, we would have plus or minus 0.05 centimeters, because we take the the limiting reading, which is 0.1, and cut it in half, and we get 0.05 for that. All right, so vectors and scalars. We've used a lot of vectors and scalars over the years, together. And what we know is scalars, you only need a numerical value. Vectors, you have direction with them. And in class, I had our students, list out as many scalars as they can think of and vectors they can think of. With scalars, dealing with distance, dealing with speed, energy. We've used many over the years. Coulombs of charge, mass in kilograms. Where you have no direction, right? Now vectors, you have to have direction, right? So, at the beginning of the year, we looked at displacement, we looked at velocity, acceleration, force, momentum, all the times that we've had to have direction. And it's very important to keep those in mind as we move forward into our review. Now with graphical addition, remember the tail to tip method, right? So if we have two vectors, we can place here vector B on the tip of vector A, and then we get the resultant. And so we've done that quite a bit. And subtraction of vectors, what we do is we take vector A, and then we will subtract, if we're doing A minus B, we're going to invert B and draw that, and then still do tail to tip there, and we can draw that. So, let's say we have vector A minus vector B to get vector C, vector B being this, we're going to invert it, and then we draw the resultant like this. So let's get some practice here. If we, add these three vectors, let's say vector A plus vector B plus vector C, we get here vector A plus B plus C, and we have the resultant there, right? Likewise, if we do vector B, then C, then A, we get the same resultant vector. And then if we have vector C, then vector A, then vector B, and we draw the resultant, we've got that there. Now, what I want you guys to do is to add this you may want to do this on a separate sheet of paper from your notes packet. When we're subtracting the vectors, we're going to invert the vectors. And we've already looked at that, A, and then inverting B to get the resultant. So I want you guys to practice this here and pause the clip and give this a try. Vector A points in the positive x direction, has a magnitude of 75 meters. Vector B has a magnitude of 30 meters, direction of 30 degrees above the x-axis. So I want you to draw vector A and plus B, and we'll add those, and then go ahead and also do vector A minus B and draw the resultant. And so, yeah, go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so with the first one, vector A plus vector B, we get the resultant. And yeah, that's from the start of A to the tip of B there. Now when we subtract them, we have to invert B, which flips it here, and then we have our resultant like that. All right, so what we did was got some practice in class looking at adding multiple vectors. In this case here, we have, person walks 16 meters, 25 degrees north of east. And then vector B is they walk 55 meters, 38 degrees east of south. And so if we were to draw this out, just for, a wide reference here, north, south, west, and east. 16 meters, 25 degrees north of east. Remember, east is where you start, and the north is where you go. So 25 degrees up. And we have our vector A, and then vector B is 38 degrees east of south, which we start on the new axis. East of south would be somewhere here, and then down like that. Now remember, essentially it's down like this, but what we need to do here is get the separate x and y components of these vectors, right? So if we draw this out, we have our, 25 degrees north of east here, and we'd have to get our vector x here, and then our vector y, and then we draw our second one here on a separate coordinate axis, 38 degrees east of south, and we get our y vector and our x vector, and then we get our total x equals total y equals, and we get those, and then we bring those together into a final coordinate axis, and then we get our blank meters, blank degrees, blank blank, as we get that. So yeah, go ahead and pause the clip and work that through. It'll be good practice, and when you're ready to check, you can hit play to continue. All right, so we get for our total, well, really just each component. Let's break that down. So for the first one, it's the adjacent side. We've got positive 14.501, and then in the y, positive 6.762, and then here in the y, negative 43.34, and then in the x, what is it? Using the opposite side, positive 33.86. So we add up our two x vectors to get our total. Our y vector 6.672 plus negative 43.34, and then we have our we have our values, our total x, total y, and then we set up our x and y on the axis. So we have our x and we have our y, and we get our resultant 60.6 meters, 37 degrees south of east is the resultant vector. All right, so another thing that we talked about in that first unit was measuring properly, and then also looking at uncertainties. And this is a critical skill working with values, because really, when you get a final result, it's only as good as the inputs that, or as good as the measurements that you have. So it's nice on your data booklet you have a copy of this, and just to review here, if you add or subtract something, you just add the uncertainties up. If you're multiplying or dividing, you set it up like this, where you have the uncertainty in that final value over that value, and then the uncertainty in first measurement over that, and then uncertainty in that over that, and then uncertainty in that over that. Now in this case, this is A times B divided by C. For our example, we're about to do with volume, all three being multiplied, and it's the same equation. Use the same thing. And then with the exponents, it's actually the same as this. It's just setting up a integer here and multiplying it by however many times that you got over here. And so we'll look at all three here. Okay, so for our first example problem, go ahead and draw out a car that travels 34.2 plus or minus 0.1 kilometers. And so based on that measuring device, we have 0.1 kilometers uncertainty. And then we have our station that we reach, and then go into an additional 20.4 plus or minus 0.05 kilometers using a more precise measuring device for that. And we want to know the total distance with the uncertainty. So yeah, if we look at that, right, we're adding these values, and so 34.2 plus 20.4 will give us 54.6 kilometers. Plus or minus a certain value. And so what we do for uncertainties then, as you can see here, is we just add the uncertainties up. 0.1 plus 0.05, and that's our uncertainty, is 0.15. So it could be 0.15 further than 54.6 or 0.415 shorter. And that's our uncertainty range there for our addition. Now, if we want to know the percent uncertainty, which is another aspect that's going to be important for us, what we do is we just take the uncertainty divided by the value, and in this case here, 0.00275 or 0.275% is the uncertainty of how much further or how much shorter the car actually traveled. All right, so what if we get the volume of this object here? Well, let's say we have our length A and length B and length C, just to make it a little easier for us as we look at the equation that we're going to use. Length A is 3.1 plus or minus 0.05 centimeters. Length B is 2.6 plus or minus 0.05 centimeters. And length C is 4.2 plus or minus 0.05 centimeters. And we want to find the volume. So we know volume is equal to length times width times height. We can multiply those, 3.1 times 2.6 times 4.2 to get 33.852 centimeters cubed. Question is, how much larger or smaller is that? And again, that's dependent on how precise our measurement was. In this case here, we're precise to the first digit. And really all of these probably should have zeros after them, because I should give you values guessing to the next digit. Because if we're precise to that first digit, we can guess to the next digit. And so yeah, we want to find out what the uncertainty is. So if you look at over here, if you're multiplying or dividing stuff, we want to use our uncertainty here, where we take the uncertainty of each value over each value, and then and get that there. So let's go ahead and set that up. The uncertainty y over y, and we'll call volume here our y value, equals uncertainty of A over A plus uncertainty of B over B plus uncertainty of C over C, again, because we're multiplying those. If we set up our values there, we have the uncertainty in our volume over the volume itself, 33.852, is equal to the uncertainty of A over A plus the uncertainty of B over B plus the uncertainty of C over C. And this could be, I could have called this length and width and height, or this actually probably be height and width or length here, whatever. And that's the values that we would have, in here and here and in here. I just made it A, B, and C just to keep it consistent with the equation sheet. All right, so when we get that, we get 0.04726. We cross multiply, and that's our uncertainty, 1.6 centimeters cubed. Now, And the next part of this that we want to talk about is the percent uncertainty. So what we do for percent uncertainty is, and you can write this out, this is a key principle here, for if you're multiplying or dividing stuff, you need to add up the percent uncertainties for each component that you're multiplying or dividing. So here, what we do is we get the percent for this measurement up here. We take 0.05 divided by 2.6, and we get our uncertainty is our value is 0.0192, or 1.92%. Next, here, 0.05 divided by 3.1, we have 0.0161, or 1.61%. And then for the last one here, 0.05 divided by 4.2 is 0.0119, or 1.19%. So to get the total uncertainty, we add them up. We add the 1.92% plus the 1.61% plus the 1.19%, and that's the percent uncertainty. And what's interesting about this is, well, we can write it out like this. We have 33.852 plus or minus 4.72%. Which really is actually just taking 1.6 divided by our original volume value. And so it's just a different way to do this. And either way is totally fine. It's just sometimes they're looking for percent uncertainty, sometimes absolute uncertainty. We need to be able to use both. All right, so let's take a look at this final example for this tutorial. We have free fall sample here where we have an object that's starting from rest and falling, takes 1.3 seconds plus or minus 0.02. Again, I should put another value here. We'll say 1.30 because again, if we're giving some precision here, I need to be consistent. We're looking to the next digit. Although it could be that it's a digital readout, and that's okay. So the initial velocity, remember we use the symbol U for that, is 0. And we want to find out, how high is this with the uncertainty. So we can set this up. The displacement S is equal to 0 plus 1/2 AT squared. And we get negative 8.281 meters is the displacement. So we've got that, and now we can look at the uncertainty. So what we do if we have an exponent is we use this here, and it's the uncertainty of the value over the value equals n, which is the exponent that we have, in this case times squared. We have this being 2 up here, and then we have a as the value itself, which in this case is time. And so if we set that up, we have our displacement here. We have our exponent 2 because it's squared, right? Time squared. We have our time, and then we have our uncertainty in time. And then when we solve for that, we get 0.0307. And but we're not done, right? Because we're multiplying by some constants. Now, if you remember what we do with that, we have the cross multiply 0.0307 times our time value, 0.2548. And remember what we have to do then is multiply our uncertainty by the constants. And once you do that, then you really have your uncertainty. So in this case here, this is our final uncertainty, which is negative 8.281 meters, plus or minus 1.25 meters. Could be 1.25 meters higher or lower based on our uncertainty, right? Because the time is only that precise, and so we can only say we're within 1.25 meters.